of not 6 degrees of freedom, basically 6 states here. Okay, you have XYZ and you have roll pitch yaw, and then you have six more states associated with this, which are their rates of corresponding rates of change. Okay, so once you have some path planning algorithm in place, the path planning algorithm essentially gives you the X, the Y, the Z, basically the entire translational path or the point in the three-dimensional space. Along with that, it gives you the heading, okay, or the yaw angle that you're supposed to maintain. In conventional quad, you cannot independently specify the roll and pitch angles independent of the XY motion or the motion in the horizontal plane. Okay, so due to which the commands do not give you, the commands are only these four quantities X, Y, Z, and the orientation angle psi. Okay, now once these commands are received, the controller, what it does is it takes the XY position, XY command, and generates the desired roll and pitch commands. Okay, so now you have your desired roll and pitch coming from the position controller. You have your yaw angle or the heading angle already given from the command itself. So all these three together make the desired attitude, and then the attitude or the orientation controller basically takes care of the fact that you meet the desired attitude. Okay, once you meet the desired attitude, that is you attain your desired roll pitch and the yaw position, then it ensures that you are maintaining your XY along, maintaining the horizontal position XY along with the heading. And then you have your Z, which is the altitude. Okay, so altitude controller again is able to combine with this attitude controller, and it gives you the final commands, which are the thrust that is supposed to be generated and the moments that are supposed to be generated. Okay, and then these, how do you realize these thrusts and moments? So the in or the actuators that you have in a quad are basically four rotors. Okay, so by spinning these four rotors up or down, so when I say up or down, basically it means either you speed up or you speed down. Okay, so when you spin this rotors up, you get higher thrust. When you spin this rotor down, you get a lower thrust. So depending on the thrust and the moments that is being moment commands that are being generated by the controller, the rotors are either spinned up or spun down. Okay, and accordingly you basically generate your torques and forces so as to achieve your desired position and desired uh, heading. Okay, so what you observe here is the attitude and the position are coupled. Okay, so if there is any change in attitude in terms of roll and pitch, there would be a definite change in position. Okay, so you cannot avoid changing position while you are changing the roll and pitch. Okay, so what we wanted was to look into some designs where I can do this attitude change and position change independent of each other, at least over some range of or some flight envelope of this particular quad. So we need to, so definitely there has to be some design changes in the
Excuse me,
original.
excuse, excuse me, Dr. Sandhya. Is the slide being changed or is it the same slide?
Sorry.
Slides are you on the second slide itself?
Yeah, I'm in the second slide. I've not changed it yet.
Okay, okay,
Yeah.
okay. Fine. Okay.
So, so we thought of, I mean, there has to be some change in the actuation so that you can decouple the attitude and orientation. Okay, so we'll, that is what we'll see. And this is a popular design that people have been working on. So this is the quad that we are currently flying with the change. So if you can see this, let me see if I can have a pointer options. Okay, I have a laser pointer. So you see these rotors here. Okay, these rotors, if you see, they are tilted. Okay, and you see, so this is the rotor. This is a motor with a propeller. So we call this setup as the rotor. And below this, if you can see, there is a black box kind of thing placed, which is basically a servo. Okay, so this servo can basically tilt this rotor. So if you consider the plane in which this propeller rotates, and let's call that as the rotor plane, so the servo can essentially change the rotor plane. It can change the tilt of this rotor plane. Okay. Now, in a conventional quad, what happens is this motor is fixed to the frame of this quad rotor, and hence you cannot tilt this rotor plane. Okay. Now, how is the thrust produced? So once the propeller starts rotating, it pushes down air. Okay, due to which you get a upward thrust. Now, with this upward, so basically this is action and reaction. If the air is being pushed vertically down, the thrust is being pushed vertically up. Okay, so in a conventional quad, with respect to the quad rotor's body, the thrust direction is always upwards. Okay, it doesn't change. Okay, now what you have is, in a conventional quad, you want to control x, y, z, which is the translation, and roll, pitch, yaw, which is the attitude. So you want to control 6 variables, while you have only 4 actuations, which are the four thrust vectors that you have. Okay, so it's an under actuated system. That is why we cannot. That is why there is a coupling between the attitude and the position. So we say that you can only control x, y, z and the yaw angle or the heading angle, while giving away the roll and pitch angle, making them dependent on whatever x and y is commanded. Okay, but now with this design, what has happened was you have made the system over actuated. Why? With the thrust being controlled by controlling the speed of this motor, you can also control the angle that the thrust vector makes with respect to the quad rotor frame. So now what you have is a force that you can control and the angle of the force that you can control. So with 4 actuators, which are the motors, you have another 4 actuators, which are the servos. Okay, so servos give you the angle and the motors give you the force, the thrust vector. So you now have 8 inputs for 6 variable control. Okay, so that is why you have an over actuated system. In some designs, what can be done is the diagonally opposite uh, systems or the servos can be coupled so that they have same angles, angular changes. Okay, then you will have a fully actuated system, not over actuated, not under actuated, because now you can control only 2 angles and 4 thrust vectors. So total making 6, and you have 6 variables. So it makes a fully actuated system. Okay, so because of this design change, you can now decouple the attitude and the position of the quad. Now, why do we want to do this? The motivation for this was, for example, let's say that you are surveying a horizontal structure, okay, with the camera mounted, let's say, on the front side, okay, and you are moving sideways. So let's say this is the x-axis. Okay, this front propeller direction is, let's say, the x-axis. You see this black module here, this is the GPS module with the magnetometer in it, and it is pointing in the forward direction. Okay, so this is my x-axis that I have set up. Okay, and I want my quad to, let's say, survey a structure while moving from left to right with the x-axis pointing towards the structure. Okay, so let's say the structure is right in front of my quad and I want to survey the structure horizontally, so I need to have a lateral motion. Now in case of a conventional quad, when I want to have a lateral motion, for the lateral motion I need to basically produce some force, and which will result in some acceleration in the horizontal direction, and this can only be done by making this quad roll about the x-axis by a certain angle. Okay, and once you do this, what will happen is the camera that you have mounted, or the sensor that you have mounted, which is along this x-axis, it will also tilt. Okay, so now while you are trying to scan a structure horizontally, you are actually not scanning it horizontal. There is some angle that is in play. Okay, and these angles can be as large as 15 degrees, 30 degrees, and so on. Okay, depending on what is the speed that you want to maintain, or how fast you want to accelerate, and so on. Okay, so to avoid that, I want my sensor to be horizontal while moving horizontally. Okay, I don't want any tilt. So in such case, what I would do is I would basically have my thrust vectors aligned in such a way that my quad maintains a zero attitude. When I say zero attitude, it will neither roll nor pitch while moving in the horizontal direction. So in this design, I can move in the horizontal direction without having a roll in the quad rotor. Okay, so that is why I can scan the horizontal structure. Similarly, let's say you want to scan you are flying above and you want to scan something right at the bottom. Okay, so you would have a camera, let's say, installed. So in such case, what would happen? When you move in any direction, your quad will essentially, conventional quad essentially encounters again the roll and pitch. Okay, so you're not looking vertically down. So what people would do in such cases is they would install gimbals to carry these cameras. Okay, and gimbals are a little costly as compared to the modification that we have done. Okay, so now with this modification, you don't need the gimbals. The camera can be fixed to the quad frame because you can achieve zero roll and zero pitch while still in motion. And with this, you can have a direct vertical view without any change in the orientation of the camera, and that reduces computational processing. When you, I mean, if you have a camera which has tilted while recording something, then you do a video processing so as to counter that tilt, and then you process this processed video. You process this processed video. Okay, but in this case, you don't have to do this pre-processing where you remove the tilt because there is no tilt involved. Okay, so this over actuated or fully actuated system, it depends on how you couple the servos, actually helps us in decoupling the attitude and the position. So I'll show you some videos towards the end of this lecture, which basically demonstrates how this decoupling is achieved and how it increases the agility of a quad rotor. So these are the initial designs that we had. Initially, we started with a wooden frame because we are testing the concept. We are very new to this, and later we moved on to another design, and this is basically the spherical balls that you see here, the gray ones. These were installed so as to test the system in a indoor Vicon positioning system. Okay. um, so now with this design, you remove this coupling here. The position does not command the attitude anymore, so you can control the position irrespective of what the attitude is. So you can have an opposite roll while going in one particular direction, which is not possible in the conventional quads or any other quad that doesn't have this design. Okay, so this is the flexibility that now you have achieved. Of course, the cost of this was increasing the number of actuators that you have in your system. So as I said, this is basically a small comparison of the horizontal motion. This is a side view of a conventional quad, and the sensor that is mounted at the bottom. If you see, this is the gray shaded area is basically the conical view that this sensor has. And once it goes into horizontal motion, it tilts. It has to tilt in the direction in which it is moving. So if it is moving in the direction that is shown here, then it has to tilt in that direction, due to which the camera also tilts. So you see the view changes. You wanted to see something down, but now you are seeing things sideways. But in this case, what will happen is, instead of tilting the quad, you tilt the rotors in the direction in which you want to go. Okay, so you observe this side view rotor here, the one with a white colored blade. So to move in the horizontal direction or in the direction shown, it actually tilts itself. So because of this tilt, you are tilting the thrust vectors and you don't need to tilt the pod. Okay, and due to which you roughly, I will not say exactly maintain your vertical view, but you roughly maintain your vertical view. The changes in the angles are very less as compared to, so they would be like 2 degrees or something, as opposed to 15 degrees change in angles when you do it with respect to the conventional quads. Okay, so this is how you basically save on. And also we did a cost analysis, and we found that the gimbals that you would use for such sensors, if you replace, the question would be, earlier the gimbals were used to keep this vertically downwards in case of a conventional quad, but now you have increased the number of actuators and you are claiming that with increased number of actuators you can save cost. So we actually surveyed that, and we found that the gimbals are more costly as compared to the servos that are being used. So making the existing system over actuated is cheaper as compared to installing a gimbal. Okay, so this is a cost feasible thing, and additional benefit of this is it's a minor alteration that you have to do. I would call it a minor alteration because to the existing conventional quad, okay, you don't have to fix the propellers onto a fixed structure, rather you fix the propellers onto a structure that can move. And for motion, you just have to incorporate these servos. So any conventional quad can be modified into a tilt quad with suitable assembly. So, so I'll explain the modeling of this particular quad, but before you go there, this is just a schematic of the vehicle. We consider this, you see the center frame, this is the body axis, this is the world frame or a fixed axis, and then we have frames that are associated with this particular rotor. So these angles that you see, alpha 1, alpha 2, alpha 3, alpha 4, they are essentially telling you by how much angle the rotor plane has tilted, and depending on that you will have your force vectors making an angle with respect to the quad rotors in the body frame associated with the quad rotor. So in this particular frame that you are associated with. Okay, so now what will happen in the quad rotor frame, earlier in the conventional design, since this angle was essentially zero, so the forces could not be resolved in any direction. It is just one component that you have which is vertical to the quad rotor frame, but now each force vector can be resolved into a horizontal force and a vertical force, okay, with respect to the body frame that you have. Now because of this resolution, this is what actually helps us, this having components of the forces in the horizontal plane allows us to basically have a motion of this quad in the horizontal plane without making the uh, entire quad rotor tilt. You just have to tilt your propellers so that you generate a component of the force in the horizontal plane, and because of this component of the force in the horizontal plane, you can have motions in the horizontal direction. Okay, and if you want motions in the vertical direction, you can. So what is happening here is, to control the XY position, the tilt of the rotors are being controlled, because this tilting can generate a horizontal component in the horizontal frame. Sorry, yeah, in the horizontal plane, and the vertical components are anyways there. So by controlling the vertical components, you can control the roll, pitch, yaw, and the Z, okay, or the height or the altitude. Okay, so how do you do that? You can, for this you can so the vertical component is again controlled by this angle. In addition to this, the vertical component can also be controlled by this speed of the rotor. Okay, of course, if you change the speed, the horizontal component also changes. So it's a combination of this speed of the rotor and the angle made by the force vectors that generates a sufficient horizontal force and a sufficient vertical force so as to meet your desired translational and desired attitude dynamics. Okay, sorry, desired translation, desired attitude commands. Now this is just a close-up view of what happens in the rotor plane. So if this is the vertical axis, the force will be vertical in the rotor plane, and hence when you resolve it in the body frame, you have a component coming along this x-axis, which is the rotor's horizontal axis, quad rotor's horizontal axis, quadcopter's horizontal axis, and the vertical axis is the ZP3. We will have a component along this. and same happens for the all four rotors. Now coming to the modeling, as I said, the forces and moments that are being generated because of the propeller are these. Okay, so the force that is being generated can be resolved into two quantities, and which is one in the horizontal direction and one in the vertical direction. This zero is coming because of the way we have resolved our frames in the x. So we say that this is y and this is z. Okay, now this force is because of the thrust generated. M is the moment that is being generated, or the torque that is being generated because the propellers are rotating. So you get so when you rotate a propeller, the torque that this propeller gives to the body is going to be in the direction opposite to the rotation of the propeller. Okay, so basically it will try to counter it. So if a propeller is rotating if a propeller is rotating clockwise, then you will have a drag force that is acting on the propeller in the anti-clockwise direction, which essentially provides the torque. Okay, this is basically a reaction torque that comes because of the rotation of the propellers. Now, because the propeller plane has tilted, or the rotor plane has tilted, not only the forces get resolved, but also this drag force, which is resulting in this torque, also gets resolved. Okay, it has components. So this is how the individual force and moments, force and reaction torques get resolved. A slight difference as far as the rotors are concerned because of the axis labeling. Okay, it just there is a change in plus or minus sign. Now you see here the forces are dependent on omega I square, omega I squared, where omega I is the angular speed of the rotor. Okay, and kf is basically the proportional constant. And here the drag force that you have, or the torque that you are getting, is also dependent on omega I squared, which is the angular speed of the ith propeller, the square of that, and km is again the what we call this as a torque coefficient or the drag coefficient. Okay, now once we have that resolution in mind, the next thing that we have is the attitude dynamics. So this attitude dynamics has been represented in the form of quaternion dynamics. You can use Euler notations as well. You can use rotation matrices as well. So you can use any applicable attitude kinematics to represent this attitude. And but this second part of the equation, that is j omega dot is minus omega cross j omega plus mb. This is anyways common to whatever you use. Okay, it is just this kinematics part where we have used quaternion in this representation. We also have representations in rotation matrix form and also in Euler angle forms. Okay, so this is your attitude dynamics. This is, if you observe, this is the normal rigid body attitude dynamics. There is no fancy or nothing changes here. Okay, what changes is how this torque is being computed. Okay, so this torque is because of two things now. One is the component of the force, and one is because of the moment. In the original or the conventional quad, you didn't have this. Okay, this component was not there. Now because of the tilting, this component comes in play. Okay, similarly the position control, this position control is again, I mean, there is again nothing different about it. This is essentially a translational position dynamics that you have for any rigid body or point mass that you can think of, and g is the acceleration due to gravity, and this entire thing is essentially written in the inertial frame or the world fixed frame. Okay, whereas if you notice the attitude dynamics is written in the body frame. Okay, so the attitude dynamics here is represented in the body frame, and the position dynamics here has been represented in the world frame or the inertial frame. And some in most literatures, you would also find that this position dynamics is also represented in the body frame, so that you have both attitude and position dynamics represented in one single frame. Okay, now here you notice the inputs MB and TB. They are inputs that you realize in the body frame. Okay, so MB is this, and TB is basically a sum of all the vertical forces that you're going to have. So RIB is trying to resolve or use the components of force that is needed for generating suitable accelerations in XYZ. Okay, in this particular model. So RIB and for propeller 1 and 3 and for propeller 2 and 4 are as given here. Okay, so this is the input that you have. We want to generate this MB and this TB so that I can have a desired attitude and a desired position simultaneously for this particular quad rotor. Okay, now you notice that this MB is dependent on the force or the thrust and the moment of the rotors, and the force vector TB is dependent only on the thrust that is being generated. Okay, so now our task is to find out this desired body force and desired body torques so that they can be finally used to compute back what would be the desired FIs and MIs, which in turn gives me the desired speed of the rotors and desired angle of the rotors. Okay, so with this dynamics, I need something that relates my angular speed to angular speed and the rotor plane angles to this TB and MB. So I need a map that maps this angular speed and the rotor angles to this forces and torques that are being considered as input in these two dynamics. Okay, so what we call them as the control allocation map. So let's see. So the components of TB and MB. So for TB, I can divide them as TB1, TB2, and TB3. And for the torque MB, I have components MB1, MB2, and MB3. Now, TB1 and TB2 are essentially considered to be responsible for motion in the XY plane, and TB3 is for motion in the Z-axis, which is the vertical motion. And this, then you have this torque, which is to control the roll, pitch, and the heading angle. Okay, so the roll, pitch, and heading angle and the Z motion essentially are used to command the rotor speeds. Okay, whereas, so this is a rough map that you have. Please notice that there are no we have not put the coefficients, the kf and km, in this particular map. However, they will appear here. This is just a way of knowing how these are affecting, in what form these forces and moments are affecting the angular speeds and the servo angles. Okay, so that is why we have just used ones and zeros and minus ones so that it is easy to visualize. Okay, but kf and km, those components can replace this ones and minus ones respectively. So the actual matrix is a little different. I might not have it here, but it gives you an idea of what happens. Okay, now the rotor plane tilt angles, they are controlled by the forces that you need to have motions in X and Y. So that is why you have two forces here. And this allocation is written in such a way that they assume that the diagonally opposite rotor angles are coupled. So they are going to be the same. So if you see here, alpha 1 and alpha 3 are going to be the same, and alpha 2 and alpha 4 are also going to be the same. So this is a control allocation that you have when your system is fully actuated. Why? Because alpha and alpha 3 are coupled, they are considered as one angle. Alpha 2 and alpha 4 are coupled, so they are considered as one angle. So diagonally opposite rotors will always have tilts of the same angle. So now you have 4 speeds to control and 2 angles to control. So total of 6 final control inputs that you actually have. So this is a control allocation when you configure your tilt quad rotor in the form of a fully actuated system. Okay, we are currently working on the overactuated system, and I'll show some videos of the overactuated system. But I cannot discuss it here because we do not have any final results for that as of now. Okay, let's move on. Now what we have the dynamics of the quad, we have the control allocation map for the quad. So now we need to come up with controllers. the controllers have to give me TB and MB. So once I get my TB and MB, then I can use this TB and MB to compute my rotor speeds and rotor angles. And once I compute my rotor speeds and rotor angles, the quad will realize whatever it has been commanded for. Okay. So now this controller that I have shown you here, MB is being generated in the body frame directly, and the thrust that we have for the acceleration in the x, y, and z direction in the inertial frame is being computed and then finally converted to a thrust command or the force command in the body frame using this. Okay, so this is a simple PID structure that I have used, but to generate this MB and TB, you can use any controller that you want. You can use robust PID controllers. You can use simple PID controllers. You can use controllers based on differential geometry. You can use sliding mode based controllers. You can use backstepping based controllers if the structure allows you to do so. You can use feedback linearization again if the structure allows you to do so, and so on. So you can use any controller that you want with the proper tuning of these gains. Okay. So once you are done with this and you have a controller in place, now you have everything with you. You have something that is generating your command, which is basically the desired translational translation and desired attitude. You have sensors which are giving you the actual position and the actual attitude, so you can compare them. Comparing these errors go into the controller, and the controller is finally able to give you this control inputs MB, which is the torque, and TB, which is the force. Now this TB and MB can be resolved into desired angular speeds of the rotor and desired rotor angles, rotor tilt angles. Once that is those desired angles and speeds are realized, the quad is able to execute its motion so that you go closer and closer towards your commanded values. Okay, so this is how you close the loop. Okay, so I've not discussed much about what the controller is because you already know how to design controllers given a dynamic model of a plant. Okay, so you have the dynamic model. You just come up with a controller with your desired performance criterions. Once you come up with the controller with desired performance criterion, you can use the control allocation matrix to finally say for these control inputs, these are the speeds and the tilt angles that is desired. So I think this is my initial flight test. Let me see if I have that. Yes. So I hope this video is visible. So this is the initial quad that we had. Here the rotors are actually coupled. The diagonal rotors are coupled, you can see, as the tilt commands are being given. So we performed a waypoint navigation. So waypoint navigation is essentially we give a set of points to which the quad rotor has to go, and the quad rotor basically completes its mission by covering all the commanded points in a particular order that was given to it. So this guy is my PhD student who has graduated, and he is actually taking it off, and then he'll put it in auto mode, which is basically the mission mode, and then the quad enters into the waypoint navigation. He's currently going to one waypoint. The second one that it is going to. This is the third one that it is going to. So this area that you are seeing for flying, this is inside our campus, and this is essentially a small airstrip that we have. So this is a huge area where we can actually test our quads. Okay, so this is where it is going to its third waypoint. Okay, let me see. Yeah, so it has come to its, I think, final waypoint, and then we'll land it. Yeah, so he just lands it. Let's move on. Uh, we since I said that this particular quad is a modification of a conventional quad, if I change my control allocation so that I don't command the tilt angles, it's just the rotor speeds that are being commanded, then you essentially can use this tilt quad as a conventional quad. So what we wanted to see is how things are for the same controller gains as far as the conventional quadcopter and the tilt rotor quadcopter are concerned for the same set of waypoints. Okay. So what we saw is that the conventional quad did follow this path nicely, and there were small overshoots at these turns. So usually the directions at which the points at which the waypoint changes. So once you reach point 2, the waypoint changes. You have to go to waypoint 3. So that this is where you change your direction. Okay, and this is a continuous process. So you tend to see overshoots. Now in conventional quad, you don't see much of a overshoot, but in the tilt mode, we saw that there are some overshoots. So possibly this gains need much some certain amount of tuning. Okay, but with the same gains, of course, we saw some overshoots. But what we wanted was to see whether there are significant roll and pitch if we compared it with the conventional quads flight. So this is basically a comparison of the roll angles. The roll angle on the left hand side that you see here is basically for a conventional quad, and you see the roll angles when the direction especially changes or when it is in motion towards a waypoint, they are as high as 40 degrees. Okay, 40 degrees, 30 degrees, and even in the other direction it goes to minus 20 degrees and so on. Okay, but if you see on the right hand side the roll angles for the tilt one, these angles are very well within 2 degrees and 3 degrees. Now this 2 degrees and 3 degrees are coming because of some asymmetry that you have during the construction of the quad. It will be exactly 0 degrees if the quad is perfect. It's an ideal quad with all the sensors being noiseless, and they being the ideal sensors as far as you can go. But these small angle changes are there because you do not have perfect sensors, and the quad rotor is not perfect, neither are the actuators. Okay, but if you see the angles, compare this 30 degrees or 20 degrees variation in case of a conventional quad when it is in motion in the xy direction with respect to this 2 degrees change in case of a tilt rotor quad. This is very small, so this 2 degrees change won't matter much unless of course you go to a huge height and you're looking downstairs. But let's say you're scanning a horizontal structure and this 2 degrees change there, it won't matter much as compared to this 30-degree change. Okay, so let's see the pitch angles. Pitch angles also have have a similar story. They are going very close to minus 30 and minus 40 degrees or 20 degrees on the other side. Whereas in case of tilt rotor, they are close to, I think here it has gone to something close to 5 degrees plus minus 5 degrees, but still a small angle as compared to what these guys conventional quads are doing. Okay, so the idea here is to emphasize on the fact that the attitude and the position in case of a conventional quad are very tightly coupled, whereas it is not the case in case of a tilt rotor quad. So with the improvement in the actuators and the sensors, you can still bring these possibly down. Okay, so I hope this is convincing enough, and if you have any questions at this stage, you can feel free to ask me, and then we'll move on to the next topic of this, where we utilize this concept to land a quad on the top of a moving vehicle. If you have any questions, please ask me now, and then we'll move on.
Hello, sir. Hello.
Yes.
You have shown the comparison of conventional quadrotor with the tilt rotor quadcopter. So,
Yes.
actually, what I would like to know is how they have been compared. Like similar parameters have been taken.
Yes, yes. So what we did was we chose the same gains for the position controller and velocity controller. So we used a PID gain structure, the default PID gain structure that comes with the autopilot that we were using. We just tuned the gains. In fact, I think, yeah, we use the default gains that are there. So all the gains and everything were kept same. And the waypoints that they were supposed to cover were also kept same. So that the environment that we create for this comparison is also the same. And then we compared it. So basically for the same set of waypoints, so this and this is the comparison that we have got.
Sir, I have a doubt, like the modeling would be different, right?
Models are different. Models are different
But
I mean,
so is there a point in comparing in this way? It's only a
yeah.
doubt, I'm just asking to.
No, that's a good point. The models are different. They are two different vehicles. Okay. What we wanted to see was, in case of a conventional quad rotor, you actually have to tilt in the direction in which you want to move. Okay, you have to give some angle. Why? Because to move in a certain direction, you need to generate a certain amount of velocity to move in the direction. And for this generation of velocity from 0 to a certain velocity, you need to accelerate. And to accelerate, you need to have a force acting in that direction, right?
Yes,
Now,
yes.
these conventional quads can generate the force in a certain direction only when they tilt. Otherwise, it is not possible. So what these tilt rotors do is, instead of making the quad tilt, they say, why not tilt the rotors to generate this particular force? Okay. So
Yeah.
now mathematically, it looks like because the tilt has now been transferred to the rotors rather than tilting the body itself to tilt the rotor, then we should not have high angles, high roll and pitch angles as far as horizontal motion is concerned. Okay.
Yes.
So what these waypoints are being, why these waypoints were taken is because we wanted to see, this is, let's say, in the y direction, then this is in x direction, then this is again in y direction and x direction. So this x direction motions usually require you to pitch, sorry, y direction motions usually require you to roll, x direction motion requires you to pitch, and similarly in this you will require to roll, and here you will require to pitch. All this assuming that you are not changing your yaw angles. Okay.
Yeah.
So if the heading is being kept always towards the waypoint, then of course you will have different rolls and pitch. But I'm assuming that suppose the quad rotor is just flying flat with the heading towards, let's say, the north direction, then what would happen? Okay. Assuming that the north is
Yeah, that's
somewhere
fine, sir.
this
Yes,
particular
yes.
direction. So
Another thing is, like in the hardware implementation,
yes.
could you give some insight on how the hardware has been implemented?
Yeah, so let me go back to my initial slides. So what we have used is, so first of all, the modification. Earlier, these motors were basically fixed on this base plate, which essentially is fixed to the quad rotor frame. So this is one change that you did. Next is, let me see if I have a label. Yeah, okay, so this is good. So these are basically the normal motors that you use for a quadcopter with the suitable size propellers. These are the servos. We have an autopilot board, which is basically the PICSOC. It's an open source board that is available, which carries the low-level computer. It's basically a low-level computer that commands the forces and moments. It does all the computings given it gets the desired position and the attitude. Then we also have a higher level computer in case we want to do some vision based processing or some other processing. And this higher level computer commands the lower level ones. The autopilot ports that are available are open source again, and you can modify the controllers in those autopilot ports as you wish. So for example, if you want to implement a sliding mode controller, then you just have to change the controller for attitude or position and replace it with the sliding mode controller instead of the regular PID controller that is available on board. And for this particular setup that you are seeing, we also had a onboard camera facing down. So this is what is the hardware setup essentially that we had.
Sir, onboard computer like Raspberry Pi or
No,
some.
this we used a Intel NUC board with a i5 processor, and I think it had a 8 GB RAM on board and a 120 GB SSD on it. It was good enough to do the video processing. So
Okay, sir.
basically, this onboard computer was running this Aruka marker recognition softwares, which are given by OpenCV for pose estimation.
So the reflective marker that has been shown here, that has got to do with Aruko marker?
No.
No.
So initially we did testings on in the indoor. We have an indoor Vicon positioning system, okay, which needs this IR reflecting markers. Basically, they are gray spherical balls.
Yeah.
And the cameras capture the motion of these balls and finally compute the exact position and the attitude of the vehicle that is moving in this particular positioning system. So for that, these reflecting markers are there. But I'll show you the Aruko markers in the next part of my talk, the ones that we used. So we used this model to land on a vehicle, demonstrating that it is easier to land these on moving platforms as compared to the conventional ones. Yeah, so reflective markers were used only for indoor testings, but then slowly we gave away the reflecting markers even for indoor testing, and finally we relied only on the onboard computer. Sorry, the camera.
Okay, thank you, sir. Thank you, sir.
Yeah. Okay, so if there are no other questions on this part, then we'll move on to the next part, which is autonomous landing on moving targets. So now the idea was, again, I mean, why we wanted to work on this tilt was also this. You need to launch a vehicle from a moving platform at some strategic locations, and then you want to recover these vehicles on some moving platform. So let's say that you're already driving and you don't want to stop because you cannot stop, and then you also want to recover the flying vehicle. So the vehicle should be able to track your moving vehicle. So this quad rotor that you see here should be able to track your moving vehicle and should land on it autonomously. Okay, all this without having any communication link between the platform and the quad rotor. So that is why we used a camera which sees down and the onboard computer that processes the output of the camera and gives suitable commands to the lower level computer, which is the Pixoc based autopilot board, and the autopilot board finally controls the quad rotor. So this is the setup that we imagined for. Okay, so the UAV has to track the target's pose throughout the maneuver. If the target is having translational motions, it should be able, the UAV should be able to track, and if it has some attitude changes, it should be able to track. We of course didn't do it for attitude changes, we did it only for translational motion. Now the challenge here is in takeoffs are, see, the critical stages of any flight is the takeoff and the landing, and that is where most of the failures happen. It's not in the cruise mode, but rather in the takeoff and the landing mode. We are focusing on landing, and we're assuming that we have a very restricted area when we are moving. Okay, for example, the top of a vehicle, it's a very small area in which you want to land. Okay, so it has to be a very precise landing. So you have to decide when you are in a safe landing zone, when you can initiate your landing. You have to keep on checking whether you are still inside the safe landing zone, and if you come out of the safe landing zone, you have to abort your landing and again go back to your tracking mode, and then initiate landing only when you come back to the safe landing zone, and so on. Okay, so this is actually very challenging. So I'll not go exactly into the algorithm, but I'll give you the overview of what we had done. So this is a block diagram of the overall architecture of what has been done. So you have your reference attitude, and you have your position controller that gives me the thrust. The reference attitude with the attitude error gives me the moment. The control allocation, then that gives me the rotor speed and tilt angles, and this is the UAV with its hardware, which gives me my inertial data from where I can compute my quad rotor's attitude and velocity. So this is the initial part that we had seen. Okay, now What is additionally used is the image of the camera, which is basically then processed by a Aruko marker detector. So camera doesn't know whether it's a Aruko marker or not. It just gives you an image. The Aruko marker detector detects the Aruko marker and gives you gives the quad a relative position, because it can only know what its pose is with respect to the Aruko marker that it is seeing. And with further processing, you get a refined relative position, velocity, and acceleration information that is used for the control of position and attitude. Okay, in this case, we had not assumed any change in attitude, so we are only controlling the position. And this position is not only given to the position controller, but also is used in the landing trajectory generator. So we are online computing the trajectory that the vehicle should follow while it is trying to land on a platform. Had that platform been stationary, you would have just come down vertically. Okay, but now since the platform is in motion, with the vertical motion, you also have to have a horizontal motion. So your height command has to be generated accordingly. You should not be descending fast, you should not be descending slow, you should be descending at the right speed. Okay, so this relative position errors can be used to generate the reference height. Along with that, it also gives the reference position command. So this blue box that you see here, which is the vision framework, and the landing trajectory generator, are the new things that are added onto the quad rotors controller. Okay. Now the Aruko marker that we usually typically people use only one Aruko marker for pose estimation, but now you can imagine as the quad rotor descends, the bigger Aruko marker will not be completely in view. Okay. Now the problems with Aruko marker is, if you have the entire Aruko marker in view, then it gives you a nice pose estimation. But if the entire Aruko marker is not in view, then it will not be able to give you pose estimations correctly. Okay, and for landing, it has to be as accurate as possible. So through trials, we could finalize that we need something known as a compound Aruko marker. It's a combination of three Arukos, a larger one, then besides that we had a smaller one, and then besides them we had a even smaller one. So this last one is something that is supposed to be visible when the quad rotor has already landed. This is for the intermediate stage of landing, and this is useful in tracking and initiating the landing stages. Okay, so this is one way of generating a compound Aruko marker. I'm not saying this is the only idea that is there in the existing literature. There are a lot of other Aruko markers. People have come up with fractal Aruko markers, where the compounding is done by putting smaller Aruko markers inside, so that the type of Aruko marker that you see doesn't change as you descend. Okay, so 3 or 4 Aruko markers can be just compounded on top of each other of different sizes. This is the one that we had used. So we printed this Aruko marker and pasted it on the platform and placed it on a vehicle. So I'll show you the ground vehicle that we use for indoor testings, and then we moved on to, I think, a Bolero, which were used for getting it landed on a outdoor environment. Okay, so these are basically the screen grabs when we are doing indoor trials. You can see that these are the 3 Aruko markers, 1, 2, and 3. So initially it is detecting this bigger one. Now as it lands, it keeps the algorithm is written such that it shifts to the next Aruko marker which is in view, and then further it shifts to the smallest one. So you see, when it has landed, when landing started, the first one was visible, but when it has already landed, you can see that the second one is now sorry, the third one, the smallest one, is now visible. Okay, now there is this small thing that you see here was basically erroneous pasting of the A4 sheet, and we realized that this was really causing a problem. So then we have to basically rectify this particular sheet. But still, with this particular small printing error, we could get away with this, at least for the indoor ones. Right? Let's see if we have the same in the outer ones. Okay, so what we did was, depending on the vehicle size, I mean the UAV size and the platform size, we constructed a conical landing zone. So once the quad rotor is at this R3T0 height, and is within 0.8 meters of this cone. Okay, so when it is right on the surface of this cone or within this landing zone, the landing command is initiated and it will continue to land. Okay, you continue to land till it is in this green conical zone. The moment it comes out of this, it resets itself, goes back to the R3 height, and then again once it comes within this 0.8 meters, it does come back. Okay, now what we found out was with the simple PIT structure, it was not able to land because with the slightest disturbance it would actually come out. So we did a slight change in the controller. We used an adaptive position controller based on the image that was being that we were getting. We tried to estimate the acceleration velocity from the Arupa marker and use that in our feedbacks. It could help us maintaining the quad in the safe landing zone. So I think I do not have the failure cases plotted here, though the failure cases were available. I think I forgot, but let's see the successful ones. I think I should have some plots. So these are again stills from the video that we were taking. This is where the landing started. This is just right the intermediate stage. So it is very close to the platform now in stage 2, and finally and the quad rotor has landed. So this is a autonomous ground vehicle that we have in our lab, which was being used for ground vehicle competition. So we borrowed it, installed it with this board and the Arupa marker, and the quad rotor comes and land exactly on the area in which the Arupa marker is. So this is for a vehicle which is moving on a straight path. Straight paths are very easy to track because there is no change in the direction. It's just moving in one direction. Okay. Next, we graduated and moved on to landing on vehicles when the vehicle is moving on a circular path. Okay. Sorry. So this red path shows the path of the quad rotor, and the dotted one shows the path of the ground vehicle in the Vicon environment. Though the tracking was done using camera, we still had Vicon so as to see what the actual path turns out to be, and hence this is the ground truth that we have. So we took off the vehicle, we took off the quad manually, and the vehicle also initiated, and the ground vehicle initiated its circular path. Now, after the vehicle reached a certain path, the autonomous basically tracking and landing system was initiated. So the quad rotor kept on tracking the landing platform till here, and from this point it initiated its landing. So if you can see, the height keeps on decreasing while it is tracking the circle, and finally at this point the quad rotor landed, and you see this, there is an overlap in the trajectory of the quad rotor and the ground vehicle, essentially meaning that the quad rotor is now on top of the vehicle and is moving along with the vehicle. Okay, so this is basically some screen grabs again from the landing of this quad rotor on a circle. This is again in a Vicon environment, but please note that the Vicon was being used just to generate the ground truth, but the control was entirely based on the Arupa marker detection algorithms. So we didn't use Vicon measurements for control. Okay, so let me see if I can. So this is the autonomous tracking that we have for indoor and outdoor platform. This is a vehicle that we had used. This is a straight line tracking. This is again a circular tracking. So this is a Bolero that we had in the flight lab. So the quadrotor is tracking this, and it will initiate to land. So my student just raised his hand to show that he's not doing anything and it is doing on its own. So this is the left hand side is the video grab from the onboard camera. It is tracking at a speed of 15 km per hour, and now it is starting to land. So we have a similar operation. So this has already landed. So we have a similar operation at increased speed of 20 kilometers per hour. We didn't go beyond this because we are a little afraid that we might crash into the vehicle. And also the processor on board could compute at a certain speed, so we didn't run. So that is also one of the reasons that we didn't go ahead. So this is a team of students which has worked on this moving platform landing. So this is another video where I mean the ones that you just saw were fully actuated systems. Now what we wanted is in case of the fully actuated systems, we could only have zero roll and zero pitch while having XYZ and other orientations. But we wanted to go further ahead, and we wanted to have any attitude possible while having any position possible. Okay, not only the zero roll, zero pitch. So for that, we first investigated, can we do it with a fully actuated setup? It turned out that it is not possible, and then we moved on to the over-actuation. So over-actuation essentially means now the servos are not coupled. So we have 4 independent servos, which means 4 independent rotor tilt angles, and of course 4 independent rotor speeds. Okay, so now the 2 videos that I am going to show you are essentially going to demonstrate a position hold. Position hold essentially means that it holds X, Y, and Z position in the 3-dimensional space while doing a attitude maneuver. Now, usually for a conventional quad, if attitude maneuver that we are going to demonstrate here would have been done, then it would have moved in the XY plane. There would have been a significant movement in the XY plane. Whereas in this video, you would see that there is no significant movement. So we have given a sinusoid roll angle to this particular quad. So the quad was rolling. So I'll just repeat this video. So the quad was rolling with a sinusoid frequency while actually initiating a landing, okay, in the Z direction. So after a certain height, we have asked it to stop this sinusoidal attitude tracking and go into a zero roll, zero pitch attitude tracking. So if you see at a height of roughly 1 meters, it would immediately hold its attitude at zero roll, zero pitch. Yeah, and then it lands. So let me see if this is another video. So after a certain height, we have initiated this sinusoid roll command. So you observe the rotors here. You see this rotor, this particular rotor. This rotor is actually having a sinusoid motion. It is trying to hold the X and Y so that it doesn't go away with the change in this attitude. Okay, so I think okay, there is one more video. So it's the same demonstration again with I think it's the same video here. So yeah, so that's it that I have. These are few of the quads that we are working on. This is again a novel quad rotor that I have not discussed, but we have worked on. So this is known as a variable pitch quad rotor. So if you see all the quad rotors lying around, the blades are essentially fixed. So the pitch angle of the blades, basically the uh, angle at which the blades are tilted with respect to the rotor plane, are fixed. But in this vehicle, the one with the green propeller and the black propeller that you see here, this is known as a variable pitch quad. This is a guy whose pitch angles can be controlled. Now, because of this ability, this can fly inverted, which is not possible with other quads. We are trying to make the tilt rotor quad fly inverted. We have mathematically established the conditions under which it will do. We are just configuring the actual system to do it. So I think within a month or two, we should be able to finally complete our inverted flight for tilt rotors as well. We have already done inverted flights for variable pitch. And this guy is interesting. Reason being, uh, this has just one engine, okay, which is one drive motor. You see, there are four motors here in all quads, but this guy has only one motor which drives all these propellers. Now, instead of varying the speed of the propellers to vary the thrust, we vary the pitch angles of these blades to vary the thrust. Now, the advantage of this is, because there is a single rotary engine, you can remove this electric motor and replace it with internal combustion engines. Okay. In fact, the group, we have a UAV group in IIT Kanpur, which is being led by Professor Abhishek and Professor Mangal Kothari from aerospace, and they have developed a engine-based quad rotor. Engine-based, we call this a variable pitch quad rotor. Now, the benefit of this engine-based thing is you have a high endurance, and the endurance is essentially dependent on how much fuel you can take. Now, the batteries that we have do not give you much of endurance, okay? But once you have a single engine concept, you can replace it with a rotary engine, which is basically a IC engine, and the endurance would depend on what is the size of the fuel tank that you have. And this is very good for high distance flights. So possibly we'll discuss this particular vehicle sometime later. I do not have anything as of now, but my student who has already graduated has worked on this, and this is the platform that he had built and landed on the vehicle. We are currently modifying this platform and the platform that I had shown in one of my initial slides, so as to have very agile quadcopter with tilt rotors. So that is all that I have, and I think I am done with my presentations here. If you have any questions on this second part or in the first part, please feel free to ask.
Sir, I think I have a question which is a bit not related to exactly what you have delivered in this talk.
Okay.
See, I am also trying to work on this area. Actually, you can say it's like a beginning only. So I have some doubt regarding, what are the, important things we have to remember while we are doing this hardware realization. Like you may, since you have a lot of experience in this field, can you give some insight into what are the important things that we have to take care of in the hardware realization?
Okay, so first thing that one has to realize is what we do in MATLAB simulations, they do not work in hardware. The reason is, when we do these MATLAB simulations or any other computer-based simulations, we have made some assumptions that there are no disturbances and the sensors are perfect and so on. Okay, which is not possible in case of a hardware. The hardware that we have shown are very cheap hardware, so sensors have significant noise. The GPS that we use has a position error of 2 to 5 meters, which is huge if you compare it with the dimension of the quad. Okay, so then You once you start working on the hardware, the first thing that you have to look into is why is your algorithm that you implemented in software not working in hardware, and that is where you start debugging it. So you have to first find out what due to what it is failing. Is it because you have a bad sensor on board, or your sensor is too noisy, or your sensor is not giving accurate results? So you have to first get them corrected. Once you have them corrected, so it can be corrected either physically or you improve some algorithms, like you can improve your Kalman filter algorithms or can use a noise filter so that you get good readings out of it. Once you have good readings, then you next thing is basically the algorithm might be good, but the gains that you used in the simulation might not be useful in the hardware, so you might have to do some gain tuning. Okay, so now to avoid all these iterations, it is always advisable that when you run simulations, you try to have the model of the quad that you are going to actually fly duplicated in the simulation itself. Okay, that is when most of your problems get resolved. And the other thing is try to it's not advisable to directly go and implement on hardware. The reason is, see, even though we build this quad in our lab, this quad would have costed us something around 50-60,000 just to build it. Okay, now if it crashes, then and propellers break, propellers are not costly, but you keep on changing them. Then after a certain number of crashes, your motors goes off. Motors are very costly. So to avoid these, what we are right now doing is we have developed a simulator which basically communicates with the actual autopilot board. So the controller runs on the actual autopilot board and sends out the control signals into the simulator, and the simulator then performs these tasks. So then now what has happened is I have come closer to my hardware realization, and then so this is known as the processor in loop simulation. Okay, so the processor or the controller is actually the system that you will use in the actual vehicle, but the vehicle that is being controlled is in the simulation. The next jump that usually people do is the hardware in loop simulation. So now your actuators will also be there in the simulation. Your model would still be in a real time system. Model would be basically a real time system running on some real time computer, but then your actuators that you have would be physically there, and depending on how the actuators are behaving and the measurements of the output of these actuators are fed in to this real-time system, and this real-time system basically executes the numerical model that you have, and the measurements are taken from this real-time system, given it to the actual controller that is in play now, the controller board that is in place. So this is what you have is the hardware in loop. So the hardware in loop system is the closest that you can have to the actual hardware. So things, if they work on hardware in loop, they mostly work on the actual hardware platforms.
Thank you, sir. One question is regarding GPS denied navigation. So,
Huh.
have you really worked on it?
No, I've not worked on it, but if you want, you can contact Professor Mangal Kothari. He is kind of expert on GPS denied works.
Okay, sir. One more question, usually we control, like in the beginning, we use joystick, and in order to make it autonomous, the second part is making it autonomous.
Hmm.
So, while making it autonomous, can you give some insight into what are the main steps in making it autonomous?
It's just your feedback. The feedback controller is essentially responsible for making it autonomous. So as of now, we what we do is in manual flight using the joystick, we just take it to a height or just take off from the ground and then we put it in autonomous mode. So the when I say we put it in autonomous mode, we ask the controller to take over everything and realize the commands that are given using the feedback control that you have.
Thank
So
you,
as
sir.
of now, that is what we have.
Yeah, yeah. Thank you, sir. Thank you.
Yeah. There are any other questions?
Sir, good morning. Actually, I have a doubt not regarding this control. Normally, in your papers, you mentioned about consensus-based algorithms.
Uh-huh.
I have I searched for that, but I couldn't get that much clarity over that. So where we can find complete
If you are
information?
starting to work on consensus-based algorithms, there are a lot of basic papers in which had come up around 2008, 2009 by people like V. Ren, Ali Jarbabai, Olfati Seber. Okay.
Okay.
So that's a good starting point to understand what actually they are and
Yes.
how they have been done. So for, of course, they are for linear systems, and then you
Yes.
can move on to specialized things.
Okay. Okay, sir. Yes. Any specific books are available, sir?
There is a book by Jeff Sama on multi-agent systems. Then there is a book by Mehran Mesbahi, which is again on multi-agent systems. So it is, I think, titled multi-agent and game theoretic. I don't remember the exact name, but if you search by these names, you should get some
Okay.
information.
Yeah. Thank you, sir.
Yeah.
Thank you, sir.
Yeah, if there is no more question, means is there any questions? Any more questions? So if there is no question, means we can wind up this session. So I would like to thank Soumya for his valuable time and sharing a valuable information to our participants. So on behalf of the entire participants and coordinators of this FDP, I would like to thank Dr. Soumya Ranjan Sahu for his valuable time. Thank you
Thank
so
you.
much, Soumya. We'll meet you again. Thank you.
Thank you. Thank you for inviting me and giving this opportunity for presenting my work. Thank you.
Thank you so much, Soumya. Thank you. Thank you, participants. We'll meet you after a break. Thank you so much. Please fill up the feedback form. Don't forget to fill up the feedback form. So after each session, the feedback form will be shared in the group. So please fill up during the time itself. Otherwise, it will be difficult. Thank you. Or we will meet you exactly at 11:30.